before we get into looking at empirical observations about S4 and A4, let me just re-emphasize the skill that was going on here with this. This is a skill that you should have. It's just a little trick for writing an arbitrary cycle, say, as a product of two cycles. We take the first element, put it next to the last object. That's your first true cycle. Then take the first element and the second to last, make another two cycle. First element and the third to last, make another two cycles, and keep going until you run out of objects to do that with. You write them in this order, but again, the function composition is in the opposite order. So it's a trick that will work to help you write an arbitrary permutation as a product of two cycles. Not unique, but it's one possibility. All right, so what we want to do now is gather data, essentially. Think and gather data about S4, set of permutations on the four objects, 1, 2, 3, 4. There are going to be 24 permutations in this group, 4 factorial, and exactly half of them, 12, should be even permutations, should be elements of A4. A4 is going to have 12 elements. Okay, so let's just go order by order here. So order 1, that's easy, only the identity. Only the identity permutation represented this way. Choosing the 1 is arbitrary. I can call this epsilon. I could also write it this way, or this way. Those are all the same 1 permutation, the identity element. So there's one element of order 1, as there is for all groups, and one cyclic subgroup of order 1, the trivial subgroup. Let's move on to elements of order 2. Thinking about the LCM condition, the order of a permutation in disjoint cycle representation is the least common multiple of the lengths of the cycles. That can help us decide what elements of this group have order 2 or order 3 or order 4, or possibly any higher order. For answering these questions. So for example, 2 cycles have order 2. Right? How many 2 cycles are possible? Well, there's 1, 2. Should I write 2, 1? No, because it represents the exact same permutation. 1, 3. 1, 4. 2, 3. 2, 4. And 3, 4. Up to reordering, which doesn't change the permutation, it's just a different symbol for it. These are the 2 cycles, right? 6 of them. Are those the only elements, though, in S4 that have order 2? Think about the LCM condition. Think about the fact that we're permuting 4 elements. What do you think, Sam? Give me another one that has order 2.
Like 1, 2, 3, 4.
Yeah, put them real close together. That's 1 permutation. These are separated. Got some space in there. Those are different permutations. Then there's maybe 1, 3, 2, 4 right next to each other. 1, 4, 2, 3. Should I write down 2, 4, 1, 3? Should I write this one down as a different one? No, because why?
Disjoint groups commute.
Disjoint cycles commute. So if I wrote something like that down, it would already be in this list. Does So that's bringing us to 9 elements of order 2. Can you think of any more? Would a 3 cycle be order 2? No. And a 4 cycle would not be order 2. Seems like we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 elements of order 2 that are going to generate 9 distinct subgroups of order 2. I think that last diagram was wrong, at least in terms, I think it was only classifying the types of subgroups, not how many there were that we saw on Wednesday, the lattice diagram for S4. I think it wasn't showing you all the subgroups, I think it was showing you the types of subgroups. So it wasn't really the full lattice diagram. There are going to be a lot of subgroups of S4. There's 9 separate ones of order 2 generated by any one of these distinct 9 elements. These are all distinct. Order 3. Cycles of length 3 will have order 3. 1, 2, 3. 1, 2, 4. 1, 3, 4. 2, 3, 4. Am I missing some? I am. How about 1, 3, 2? And 1, 4, 2. And 1, 4, 3. And 2, 4, 3. How about now? You think I'm done? I claim I am done. Remember, any of these can be written in really 3 different ways. For example, 1, 2, 3 can be written as 2, 3, 1. Or 3, 1, 2. Those are the same permutation. Same for the other 7 of them. There's 8 elements of order 3. How many subgroups of order 3 would there be? At least cyclic subgroups. Although it does turn out that any group of order 3 has to be cyclic. How many cyclic subgroups of order 3 and therefore subgroups of order 3? If you've got 8 elements of order 3. Somebody must know it. Be brave.
Is it 8?
No. I'm glad you tried anyway. Any element of order 3 is going to generate a cyclic subgroup of order 3 that's got 2 non-identity elements, both of which have order 3. A squared has order 3 as well. Right? A squared squared would be a to the 4th is a squared cubed, a to the 6th is e. It's the same as a cubed squared. That should be enough to help. What should I put here?
4.
4, yeah. Divide the number of elements of order 3 by 2. Because any cyclic subgroup generated by an element of order 3, any cyclic subgroup of order 3, will have to have 2 generators. So for example, the cyclic subgroup generated by 1, 2, 3 includes the identity. It includes 1, 2, 3. And if you square 1, 2, 3, what do you get? You should get 1, 3, 2. If you think about it. These 2 elements with the identity form 1 cyclic subgroup of order 3. These two elements with the identity form a second cyclic subgroup of order 3. These two form a third cyclic subgroup of order 3. These two with the identity form a fourth cyclic subgroup of order 3. And it is true, I'm telling you, that any group of order 3 has to be cyclic. So in fact, those are the only groups of order, subgroups of order 3, not just cyclic subgroups. Subgroups of order 4 don't have to be cyclic. But elements of order 4 do generate cyclic groups of order 4. Did you catch that? Say it again. Subgroups of order 4 don't have to be cyclic. There are non-cyclic groups of order 4. We've seen in the past that there are, like U8 is a non-cyclic subgroup of order 4. Every element was its own inverse, 1, 3, 5, and 7. However, any element of order 4 does have to generate a cyclic subgroup of order 4. Powers of that element. Cycles of order 4, like that, of length 4 will have order 4. There's one of them. There's another. How many should there be overall here, by the way? Yeah, there should be 6 of them. So far we've accounted for 18 elements up to that point. And yeah, there won't be any elements of order greater than 4 in S4. In S5, there are elements of order 6, however. But the subscript is in general not an upper bound on the order. It is for S3, S2, S3, and S4. But S5 does have elements of order 6. A 2-cycle combined with a disjoint 3-cycle. We have order 6 in S5. Well, so we should get 6 things here. We've got 2 so far. Let's see, what else do we have? How about this? Guess I need another one with the 2 in the second spot as well. Six elements of order 4. How many cyclic subgroups of order 4 are there going to be? How many generators does a cyclic group of order 4 have? What's Euler phi of 4? 2. Every cyclic group of order 4 has 2 generators. The generator itself, the initial generator, A, and its cube, A cubed. You've got to divide 6 by 2 here as well. There's 3 cyclic subgroups of order 4. What would be the cyclic subgroup generated by 1, 2, 3, 4? It would include the identity. It would include 1, 2, 3, 4. 1, 2, 3, 4 to the second power. Compose it with itself. Let's see. 1 would end up getting mapped to 3. 3 would end up getting mapped back to 1. 1, 3, 2, 4 would be 1, 2, 3, 4 squared. Cube it. 1 would get mapped to 2, then 3, then 4. 4 would get mapped to 1, then 2, then 3. I'm cubing it. It's under 3 movements here. And 3 gets mapped to 4, then 1, then 2. There is a cyclic subgroup of order 4. The cyclic subgroup generated by that element is also the same as the cyclic subgroup generated by this element. These two things kind of go together. One is the cube of the other, and vice versa. Are there okay, so we focus on cyclic subgroups. Are there any non-cyclic subgroups of S4? Turns out there are. There are non-cyclic subgroups of order 4 made by combining appropriate elements of order 2. I won't take the time to figure out an example of it. There are other non-cyclic subgroups of S4. A4, for one thing, consisting of only the even permutations. What would those include? They would include these three. Those are even. This red marker is that's a bit better. Those are even permutations. Any 3 cycle is actually even, right? Because, for example, 1, 2, 3 can be written as 1, 3, 1, 2. Product an even number of 2 cycles. These are all even. And the identity is even. Is that A4? A4 has 12 elements. 8 plus 3 is 11 plus 1 is 12. That's A4. That's a subgroup order 12. Not cyclic. And there are other subgroups too. We'll look at those maybe a little bit on Monday. So we can answer these kinds of questions here. We can try to make the subgroup lattice. I think I won't take the time to start that today because I do want to start talking about isomorphisms. Okay? So you can see this does get kind of complicated. Imagine trying to do this kind of thing for S5 or S6 or S7. It's doable, but it would take a while. S7, remember, has 5,040 elements in it. Yikes. Maybe instead of writing down the elements of given orders, maybe we would just figure out some way to figure out the number of elements of the various orders. And in fact, some of the completion problems are of that type. Instead of just writing down the possibilities, you think and use the multiplication rule, the fundamental counting principle, to figure out the answer. But you do need to be careful for the fact that these things can be written in different ways when you do that. Probably do an example of that on Monday as well. All right, for the rest of our time, let's start talking about isomorphisms. What are they? An isomorphism, first of all, is a function. Call it phi. This is not Euler phi, okay? This is not Euler phi, it's another kind of function. It's got to be one-to-one and onto. From a group G to a group G bar, that G bar is supposed to be higher. To a group G bar. That is one-to-one and onto it, and operation preserving. In the abstract, you write it this way. Phi of A times B is phi of A times phi of B for all A and B and G. You have seen something similar to this before in your mathematical past with linear transformations of vector spaces. You should have seen equations like this. Vector spaces are groups if you only think about the addition and ignore the scalar multiplication. There are Abelian groups under vector addition. And this property that you saw about linear transformations in linear algebra is exactly this property, just with additive notation rather than multiplicative notation. There was an extra property in linear algebra that did deal with scalar multiples and pulling them out like that. That's not what we're talking about right now. We're only talking about groups, not vector spaces right now. We will talk about vector spaces in a couple months. Note on the left side, the group operation is in G. meaning the A times B. And the right-hand side, the group operation is in G bar. Phi of A times phi of B. Phi maps G to G bar. This is G, and this is G bar. Phi is mapping from G to G bar. So A and B are elements of G. Phi of A and phi of B are elements of G bar. This operation preserving thing is saying if you multiply A and B first to get the product A times B, and then map that over into G to get the point phi of A times B, you will get the same thing as if you map A and B individually and then multiply those things. And this turns out to be enough to make sure these groups do have the same structure. And if they're finite groups, the Cayley tables are going to be identical, at least if you put the elements in the correct orders on the left side of the Cayley table and on the top. You can match the Cayley tables up, and the book discusses it. In such a situation, we say G and G bar are isomorphic, and we write one of these things. Our textbook writes that. It's like G is approximately equal to G bar. No, don't say approximately equal to. Say isomorphic. The way I learned it was actually this way. Or it might have been that way, I forget. One of these two ways. You could write it like that. Maybe even once in a while you'll see somebody write it with 3 lines. I wonder why we're using this notation. Maybe isomorphism is an equivalence relation. It is. On what set? Equivalence relations have to be defined on sets. Is it an equivalence relation on G? G bar? No, it's not actually. It's an equivalence relation on the set of all possible groups, which is some humongous set. I can't really, it hurts my brain to even think about it. It's a set of all possible groups where each point of the set is a group. And every group is in the set. Yikes. That's the set it's an equivalence relation. Examples of isomorphisms. Exponential functions actually can be isomorphisms. At least if you've got the right groups that you're thinking about for the domain and the codomain of the function. The real numbers under addition as a group turns out to be isomorphic to the positive real numbers under multiplication as a group. And any exponential function except 1 to the x can be an isomorphism. I think that's right. Say you take 2 to the x. Define phi from R to R plus by phi of x equals 2 to the x. That's going to be an isomorphism. To check the operation preserving property, well, okay, first of all, I should mention that it is 1-to-1 and onto. Its graph, of course, looks like this. The domain is this thing down here, and the codomain is this up here, not including 0. It's 1-to-1. We're not really proving that, but it is. It passes the horizontal line test. No horizontal line goes to the graph more than once. I'm just trusting that that's true. And it's onto every positive real number, y, has an input that gets mapped to it. In this case, it would be log base 2 of y. Gets mapped to it. Because 2 to to the log base 2 of y would equal y. And it's operation preserving. Careful, the operation in the domain is addition, and the operation in the codomain is multiplication. I want to show phi of x plus y equals phi of x times phi of y. And it does by properties of exponents. 2 to the x plus y equals 2 to the x times 2 to the y, which is phi of x times phi of y. And x and y are arbitrary. The operation preserving does need to work for all elements of the group. So that's one example of an isomorphism. And by the way, it can go back the other way. You can define, call it psi, say, from r plus to r by psi of, I'll go ahead and call it y, equals log base 2 of y. And properties of logarithms would allow you to verify that's operation preserving. You'd end up verifying that psi of x times y equals psi of x plus psi of y. Psi is the inverse function of phi. Here, by the way, I could have written phi inverse. Z onto an arbitrary infinite cyclic group, and vice versa. In fact, you can even have an isomorphism of the integers onto a proper subgroup of itself. For example, subgroup generated by 2, all the even numbers. Take an arbitrary integer and map it to 2 times that integer. That's going to be your isomorphism. And it's operation preserving because of a distributive law. The operation here is addition in both cases. Interesting. Z, and in fact, any cyclic group, any infinite cyclic group, is isomorphic to proper subgroups of itself. Infinitely many proper subgroups. It's also isomorphic to this, and this, and this, etc. Weird but true. Once you get used to it, it's really not so weird. Zn turns out to be isomorphic to an arbitrary cyclic group of order n. Like that, where A has order n. Map your arbitrary K. That's an element of 0 through n minus 1. This is an element of. Map it to a to the k. That turns out to be an isomorphism. I hope that makes some intuitive sense. The powers in arbitrary cyclic groups always acted like the integers themselves in Zn. U10 turns out to be isomorphic to Z4, it's cyclic, and vice versa. D3 and S3 turn out to be cyclic in the way we saw with the Cayley tables and the way I described as far as the mapping goes in lecture A. Okay, these are examples of isomorphism. There are surprising ones, shockers. You would not expect. Turns out the real numbers under addition are isomorphic to the complex numbers under addition. What? How can that possibly be? The real line and the complex plane isomorphic as groups under addition? It's kind of a shock. And the textbook mentions, the author mentions that it's pretty hard to prove, actually. You need some advanced techniques. It also turns out, kind of shockingly, that the set of all non-zero complex numbers under multiplication is isomorphic to, this is the unit circle. under multiplication. S1 stands for sphere of radius one, dimension 1, meaning it's a circle. And in fact, we usually take it to be the unit circle. In the complex plane, if you multiply two numbers in the unit circle in the complex plane, you get another number on the unit circle. They turn out to be isomorphic as well. There are a bunch of properties. I'm not going to say what these are today. We're out of time. About isomorphisms related to group elements, and in fact related to groups themselves. You should study. We'll talk about them some on Monday. You will not need to know all of Chapter 6 for the exam, by the way. I will highlight the main points to know for the exam. See you then.